Dr. Vijay.
Yes, sir, it is visible, sir. Please,
Mm.
you can start, sir.
Okay, I was waiting for your instruction actually. Okay,
No, 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 sir.
okay,
Please
thanks.
start, sir.
So, good afternoon, participants, and this is the second lecture that I have, and this is again the same way. Uh, because in the morning session, in fact, it was not morning, but a noon session. I had discussed some of my work using the signal processing tools or even the AI techniques or the machine learning techniques, for power system signal related issues actually. And that's the same way in the second part of this talk. Uh, I have some more critical study which has been carried out by by our PhD students because uh, one of my PhD students in the project she was supervised with two of our faculty members, and one faculty member is in presently he is in IT BHU, Dr. Soumyaranjan Mohanty. So we had the DST project, and then we had some critical study related to the islanding and power quality in the renewable systems. So with that DST sponsored projects, we had the hardware setup available in the lab, and we developed some signal processing tools or the machine learning tools. And we move for real-time detection because in the earlier session which I discussed, all those analysis, all those study, they were as offline analysis. uh, but then in this part what I will discuss, it is as a real-time analysis. So and we have more critical issues, and thus the topic of the talk which I have referred, it is, I have said, evolving disturbance. And this evolving disturbance, we had one paper recently, it was published last month, in month of August, and this work was again done by one of my PhD students, and so this is what we would like to present, and then discuss about what is evolving disturbance and how we can have its real-time detection and as well as a classification. So move to the next slide, and as introduction, I have to say that because if you consider a complex integration of renewable resources, and then it is possible that some in some situations you will have the power supply interruptions and the power quality related issues, which are actually because of some in some way or other initiated due to fault event in the DG system. So that means you have some event, for some physical event, right? It could be fault, because normally the fault event, it is unintentional, and we do not and moreover fault we cannot predict also, its occurrence we cannot predict. So if there is a fault or maybe some intentional event occurrence, it could be, let's say, energizing the transformer or so, no, or maybe de-energizing transformer. And that's because when you say the transformer energizes, it means that you are connecting a line or disconnecting the line. And as such, uh, there will be an issues in a complex DG system related to the power quality. And thus there has to be some way how we should be able to minimize the risk associated with the poor quality, and that will be the first step. And that's why we need to have some kind of real-time detection approach, or some kind of a real-time diagnosis of these disturbances. Because unless we have the real-time detection, we cannot achieve the real-time diagnosis, right? So thus our objective has been towards the detection part rather than diagnosis and then mitigation. That is not we have discussed in this part, or not we have carried out in our work, but we have only focused on real-time detection. As I said that when we have a large number of renewable resource integration and mainly through the power electronic devices, then the issues related to the power quality and penetration, and again with the penetration level, the issues will get increased multiple times. That is one thing we have to keep in mind. And next one, the as introduction to the problem was unintentional islanding, which was a threat to the DG network. And this event occurrence is associated with power quality degradation and then out of phase reclosure. And then based on with looking into this point and then this point, we move on to work on how we can have the real-time power quality monitoring approach, because this will help to reduce the time for the power engineers and as well as adopt some remedial measures if we want to address these power quality related issues here. Uh, I hope I'm audible to all the participants. If anybody can confirm. Yes, please.
Yes, sir, you
Yes,
are
sir, you
audible.
are
Sir,
audible.
audible. Audible, sir, audible.
Thank you. Thank you. Because mainly when we do the online kind of this attempt, so we need to be confirmed that okay, the on the other end it is clear, and then we are able to present ourselves. So thank you for that. So what are the evolving events? And in this slide, I have listed some of the examples that we observe. In fact, when I look at the problem, I was just referred some papers, and there I came to understand that there are, in some cases, evolving occurrence of events, and that could be a new form of the power quality issue. So, and thus, if I have to say some of them, it includes the voltage sag, uh, occurrence in the one part of the network because of anti-islanding scheme. So you have an anti-islanding scheme and voltage occurrence in some other part of the network, right? Then there could be energization of transformer, which connects to the renewable resource through a weak network, and following the occurrence of unintentional islanding. So that means, let's say that because your DG systems, right, and it's also connected to the utility grid. So let's say that in one part of the network, one part of the line, DG line, distribution network line, I mean, so there is a unintentional islanding event, right, takes place. And again, let's say that in some part of the interconnected network, you also have an energization of transformer. So if these two different events does takes place one after another, all right, then this could be an example which we call it as evolving events. Then because of this energization, you may come across, experience high inrush current by the transformer, drawn by the transformer, and as such it will result into drop in the voltage. That will significant amount of voltage sag will take place. Another example could be, let's say that you reconnect a energy source. That means, let's say you have a renewable resource and you try to reconnect via transformer, and then again through a transformer you also have an underground cable or maybe capacitor also. That may also cause to a resonance condition, and then because of which you may have a over voltage, but again it will be a temporary over voltage. So this is a voltage check. So let's say you had some disconnection and then reconnection of the power source, and then because of that, resonance takes place in the network, and this results into voltage swell. So here you have two different activities. One is the islanding and then reconnection, and then you follow that you observe some disturbance in the voltage signal. So this is another consequence that you come across. So this is a voltage swell here. Then same way there could be multiple events occurring in succession. This is what I refer to here. So evolving events, actually those events which occur in succession, that means in time series we observe them. So different evolving disturbances occurring in the same sequence of time series. So we want to detect those kind of challenging events in the system that we are likely to have here. Why it is important? Because several DGs, when you have being interconnected, uh, other than islanding, it will be also important to quantify the power quality, because you have an islanding, and now and then again you find that power quality is also associated with the islanding event here, right? So thus, and we do not know, because we don't have any information. There is an uncertainty in the connection and the disconnection of the renewable resources. All right, that is taking place to the transformer, or maybe initiation of any fault leading to either DG or the load trip, because there is an uncertainty in all these events that may take place here, and then which will be followed by the clearance of the fault, or maybe you have a capacitor switching in some other part of the network here, right? So these are all unintended consequences related to power quality issues here. So that's why this is important, why we want to address the evolving disturbances here. Now, if one class of the power quality event, right, let's say the sag or the swell, if it can be known, if you can determine instantaneously, then it is possible that you can adopt that, because this takes place, power quality disturbance takes place because of some physical disturbances. Then in that case, it is possible that you can apply a remedial action, all right, before the violation of the limit takes place, because we have the standards defined that the sag should be this much limit in magnitude, swell should be within this much limits here. So there should not be any violation of those power quality signals here, right? And thus we should be able to detect them and then apply some remedial measures. We need to have some remedial measures in action here. Now, challenges suggest in island detection problem, which involves evolving disturbance. As I said, that means let's say the fault following by islanding, or the interaction among the various DG systems equipped with anti-islanding protection when islanding occurs, that which takes place. So thus we need to, with this objective, uh, we wanted to have some kind of technique being developed for which we are able to have a real-time analysis, a real-time detection approach and a classification approach here. So we move to the next one, and for this we have some advanced signal processing techniques and pattern, that means machine learning techniques applied here. Mainly we have considered the least square support vector machine as one of the technique here in the study. So thus we understand that these such evolving events, they have the signal properties which is more complex, right? And it may not be very easy to be to understand their properties actually, or to be identified. That means the event associated to evolving occurrence, they cannot be easily identified actually, and thus classified here. So thus we have some advanced techniques like shifting process. Maybe in the later slide, I will discuss more in detail about this technique. So shifting process of the empirical mode decomposition, that is one of the technique that we have used in the study. Uh, with this we can obtain the intrinsic mode functions and thus the residue, and this is a well-defined procedure here. Now, there is another variant here. This is the assemble empirical mode decomposition, which is again a powerful tool which overcomes the limitations of the conventional EMD, and thus it helps to achieve an accurate detection here. Then the third, there is another variant you can say of EMD, in fact perhaps EMD. So thus in fact the disadvantage of the EMD is that we cannot have orthogonal decomposition of the signal, and thus it is not possible to have adequate decomposition of the IMF, because IMF, I will discuss in later slides. This IMF, this should be monotonic component. Actually, this should have monotonic frequency component, and that could not be easily achieved using EMD. And and again, we observe that there is a energy leakage between the IMFs. So that means some information loss takes place in the decomposition of the signals here. However, with the orthogonal applied, we can obtain more accurate IMFs here, and thus this helps in energy preservation, or that means the leakage here, preserving the energy leakage by adopting the orthogonalization process, right? So move to the next slide here. I think sorry. Uh, uh, Here, I just wanted to give an illustration. What is the oscillatory signal which is likely to have here? So, if I say signal, so you have a signal here, right? Now, this signal, what you find here that it is actually a superimpose. So it is superimposed of fast oscillating signals, and then again a somewhat slow oscillating signal here. This one. So thus a signal can have a superimposition of high frequency component and high frequency component which is oscillating at much higher frequency, and some even low frequency component which is slow oscillation. And then again, there could be some more superimposition of the signal between the slow and the fast. So as such, the signal, the test signal, we can have it as
कुछ नहीं
high
कटौती
frequency
हुई
part,
कटौती मेन कटौती करनी होगी
which can be as high frequency component, which will refer it as intrinsic mode functions, and then another one as low frequency part, which we call it as residue here. So I will explain later in the slides. So now this decomposition of the original signal into intrinsic mode functions at several levels, and then finally obtaining the residue, that is actually a iterative process here. So we do the iteration on the slow oscillations component here, which will be considered as a no signal. So I explained it later slide, and that will be as a we can write it as a residue part, this D1, or maybe it will be some other, in fact, intrinsic mode functions part, high frequency component, and then some another residue here. So this is will be an iterative process here for different levels here. So as in this case, so you can see here the original signal decomposed into IMF and residue. Then further, this residue is further decomposed into IMF and residue. And then again, this residue is further decomposed into IMF and residue. So this we do, this we have the iterative till we are able to decompose the several level of IMFs, D1, D2, D3, D4, and so on up to N. So several level of, and that means N level of IMF we have decomposed till you get a DC decay component here, the DC component finally, which you are able to achieve here. So with this, we actually decompose a complicated set of a signal into a finite number of IMF here. I will just explain with this one. Now, what you have it here, let's say that this is a signal here, or And here you can see, you can find that this signal has several frequency component present here. Now, with this step, uh, with the zero iteration, what we do, we take out the peak, the positive peak. That means the positive envelope. We take the peak of the envelope here, positive peak envelope here. All right, we have taken the first, that means the peak here of the positive, and then we obtain this one. We obtain this signal here. Then we go for low minimum, this one negative side, negative envelope. We get the peak of negative envelope here, right? And then we get this signal now. And then what we do actually, we take, that means you have an upper envelope. This is blue line gives you an upper envelope, and then this red line gives you a lower envelope here. That we call it as, you can say it as a local maxima here, because this is the upper envelope. It gives you local maxima, because this is local maxima, this is another local maxima, this is another local maxima, right? Same way, we have a local minima here also. This is one local minima, this is another local minima here. So we have a local minima, that is for the lower envelope here, right? Now, then we take an, what to say it as, this, we obtain a pink color signal, as you can see here, that, right? So we have the sum, in fact average here we have obtained. This is your IM of 1 here. All right, so we obtain an IM of out of these two, upper envelope and the lower envelope here. So we have obtained now first IMF here. So this pink color gives you first IMF after zero iteration here. And then with this IMF, you also obtain a residue here. So this is your residue. So this is zero iteration. Now in the first iteration, you consider, now for the first iteration, you consider this residue as your original signal. So you can see that this residue is now your original signal here now, right? And then same way, so you have your IM of 1. So for the first iteration, you have an IM of 1 and you have a residue here, or a residue as well. So thus for the residue, you again obtain the positive peak here. So for the upper envelope, and then you have an upper envelope curve obtained, and finally you can get it for residue. So this process we keep on doing till we are able to have the IMF, that means the original signal being decomposed into several IMF, several intrinsic mode functions which corresponds to a particular frequency component. So that means it is possible that the first IMF will correspond to highest frequency component, the next IMF will correspond to the next highest frequency component, and the last one, and in fact the lowest, the n minus 1 IMF will correspond to the least frequency component, and the last signal component will be your DC decay component, that is your residual component here, right? So with this background, so we move to the technique that we had applied. Now, we have actually used energy preserving assemble empirical mode decomposition. So in fact, the traditional EMD, which I have discussed just now, it is associated with some disadvantages, and mainly it is because it is possible that if I go back, it is possible that when we have more complex signals, so this IMF which we achieve out of the upper envelope and the lower envelope, it does not correspond to a, it is not actually a monotonic component. So it may be possible that you have more than one frequency component present in the signal. All right, but it is very much essential that the decomposed IMF, each IMF decomposed should correspond to only one frequency component. right? So it is very important. And thus in a more complex signals or a non-stationary nature of the signals, and even with the presence of noise, in that case, the IMF which is decomposed, they are not exactly the monotonic component. And that means it may have, let's say it may have frequency component corresponding to 28 hertz, and it may also have another frequency component corresponding to 22 hertz. So thus 28 hertz and 22 hertz, they are very close, right? But you find that there are two frequency spectrum being observed for this signal when you do the analysis, spectrum analysis. So that is not desirable when we want to have pure understanding about the signal. As such, we have a little bit advanced one. So here we have the energy preserving. So what we do here, let's say that this is your disturbance signal, a time series disturbance signal, and then it is decomposed into first IMF here, and then the residue part here, where you have a non-zero signals IMF and residue part. These are the first IMF, right? And then we have it later on. We consider, let's say, this signal. We consider, in fact, we refer it at R1 and another part as this one here. So we want to have the decomposition of the IMF into orthogonal form. So we write in this way, right? And such that this signal and this signal, they are orthogonal to each other here. So that means this part and this part, they are orthogonal to each other. And then we do some manipulation or rewriting the equation 1 here. So we write the complete disturbance signal as this one, so equation by 3, where you have the orthogonal assemble IMF given by this one, this relationship. So in the next stage of decomposition, we apply the Gaussian's optimization mean and for the lower mode of oscillations, so as to orthogonalize the EIMF and thereby obtain the residue as well, right? And so that you have the proper, you can say the property being maintained for each orthogonal assemble IMF level, and as well as the residue, so that the uh, energy leakage is preserved here between the IMF, decomposed IMF here. So following the same procedure, we have another part, decomposed part, orthogonally decomposed part, and we write it further. So thus we do the orthogonal test. So we do the orthogonal test up to ON to ON plus 1, where the residue this term part is not 0. And thus from equation up to from 1 to 6 in general form, we can write in this way here, right? And finally, in the Hilbert space, we will refer, let's, because there could be different disturbances signal. So we can refer at D, D1 and so on. That could be the set of the vectors. And for each set of the vectors, these conditions have to be satisfied here. So following that, I mean the previous equation, we obtain the square of the norms so as to know whether the energy leakage is preserved or not. So we do that. So that means we need to test the energy content of the signal. So that part we have that. So that means the energy content of the original signal and the energy content of the decomposed signal, orthogonal decomposed signal, that should be exactly matched. Then it only we say that energy leakage is being preserved. And next, for each orthogonally decomposed IMF, we obtain the Hilbert transform following the convolution on the signal here, orthogonally decomposed signal here, right? And then we can write the analytical signal as the real part and or real part of the orthogonal decompose and the imaginary part of the orthogonal decomposition. So with these assemble techniques of EMD, we have developed the algorithms here, and this is the flow chart for the algorithm which we have applied in our study. So we have the disturbance signal. In fact, we have referred what are the equations in each step that has been applied here. We can. So for this evolving disturbance, we have the decomposition into IMF, and then extracting the orthogonal part here, and then we had used, because signal is decomposed into several orthogonal IMFs, right? But it is also very important to select which IMF to be considered for your analysis here. And for our case, we have used the significant high frequency component here. So that's we checked that which orthogonal IMF has the highest frequency component. So we checked that, and then following this, we had applied Hilbert transform to the signal, selected orthogonal EMF. Yeah. And the last next step was to have the calculation of some features, statistical features, so that we can have the classification of those disturbances, those events, using the least square SVM. Yeah. Right. So I move to the next slide, and this slide tells you some information about the hardware setup which we have used in our study. And you can see that we had the rooftop PVs, and then their interface subsystems. We have the converters, boost converters, and the control related part, and then another converters for the grid connected sites, and then some switches, and then we also had some load, and then again because this PV was have to be grid connected, because we want the islanding operation at this point. So it is the switch opening or the closing. So that is the islanding event has to take place here. So it has to be through the grid here. So we have actually uh, in fact a grid emulator. So a grid emulator is nothing but inverter, right? It is inverter based grid emulator which has 5 levels here. And then we had the different uh, control part applied in each of the stages here. So you have the converter, boost converter control part, grid side converter control part, and then again, because this is the grid side part, so there has to be a reference from the grid side. So we do the PLL here, phase lock loop, for the calculation of the phases to synchronize the grid side converter with the grid here, main utility grid here. We do that part. And then again, for this control, grid emulator control, we have another control strategy here. So that is this some information about the size of the system. We had it in a study. We had some what is the power maximum, and then some parameters of the module which we have used, right? And these are some photos of the controller or the hardware setup in the lab here. And then the complete description about the integration of the subcomponents is shown in this slide. So we have the rooftop PV, and then the boost converter, and then we will have also filter included, and then the controller part, gets that controller part, then again through some PC. And then at the PCC point, we have a load also here. So we have a dynamic load. And then this side you have a 5-level grid emulator inverter base, right? And then it's control part. And then we also have filters on this converter, and then the control part here to another computer. So that is the complete description about the hardware setup which we have considered in the study here. And This slide shows this is this is not a new contribution for the control implementation. In the study, I think many of you will be aware that what is the control approach we apply for the converter. So we have the three-phase signals here, right? And then we convert into alpha beta transform, we transform that, and then these are we apply the q-axis controller and d-axis controller, that means inner loop and the outer loop controller. And this is for the voltage control on the grid side converter here. So the purpose is this one. So the voltage here, it has to be as per the desired value. So that is the controller scheme. That is the existing controller scheme we have adopted here in the study. Now, since we wanted to have the real-time detection part, so right, so that means if you have some initiation of the event, right? So in that case, it should be detected by your techniques here. So for that, the system is your hard. That you have a physical system, and you have your physical controller as well, right? But the algorithm, the control algorithm has to be developed, and that development we have it in FPGA blocks here. So this is the this slide shows you how we have the ID reference generated from solar VDC control part, which was implemented in FPGA for grid connected mode here. So we have all those blocks developed in FPGA. Right? And then the same way, because when the system switches over to the unlanding mode, then again there has to be different control scheme, and thus for the unlanded mode, the control scheme was similarly implemented in FPGA here. So it was all real-time controller design actually, basically, right? And this is the slide which shows the uh, one is the physical system, and then physical controller, and then control algorithm to be implemented in FPGA, right? And then you want your detection algorithm. As I said, we have the signal processing techniques or the classifiers, least square SVM techniques, right? So even those algorithms for which I have shown the flow chart in the previous slides, so they have to be also implemented in FPGA, and thus because we want the real-time approach. So as such, we have the EMD techniques being implemented in FPGA here. So these are some of the steps of what is the approach that we have applied. How the complete mathematical equations were configured in the form of FPGA blocks. It is actually illustrated in this slide here. So in fact, this is right from step one, you have the signal acquisition, and then we introduce some lag, a delay here, and then we do some addition, in fact, multiplication, and then we store the signals, and then we apply the EMD procedure. That means EMD approach, that means decomposition of IMFs. And then we take the mean because we want the upper envelope and the lower envelope, all that part we do. And then last one, we apply the Hilbert transform on each IMF here. So up to the stage, this one. This is actually EMD technique. Then the more advanced one, energy preserving part. There are some additions in the step, and that is also included after this one. So before applying the Hilbert transform on each IMF, we go for orthogonal decomposition here, orthogonal part here. And then finally, we apply the Hilbert transform on the orthogonal decomposed assemble IMF here. And that completes your EPEMD stage. So we have EMD stage and EPMD stage implemented in your complete FPGA blocks. Yeah. Similarly, this slide indicates how we have actually developed the basic EMD technique in the FPGA, which actually I have referred here. So if you refer to the step second and third, it is the EMD procedure in this block. So it is this one here. So in the EMD technique, what we are interested to know between the two samples, as I said that we want to have the envelopes. All right, so we want to know what is the maxima, two maxima and two minima. We get that. And this, so those maxima and minimum points we refer, and then we obtain an envelope out of it here. And then we obtain have a minimum extraction, and then we check whether it is an IMF or not. We do that because the condition for IMF is that it should be of frequency component here. There should be frequency component present here. And if this is satisfied, then we consider the first decomposed signal to be as first IMF here. And that will be as an input signal for the next stage, for the next stage in the iterative process. And thus we do the complete iteration for the remaining IMFs here till we get the final residue here. So that part we do here. And this is the complete illustration that we have applied for EMD development in a FPGA block. Now, in fact, extractor IMF is corresponding added for assemble process, because if you remember in the previous slide, I have said that up to this part here, we have the EMD here, right? EMD, and then it comes to the assemble part. So we do that, right? And then in the next stage, the amplitude, we take the amplitude and apply the Hilbert transform, so that we are able to know about the impulsive response here of the signal. And that is by as Hilbert transform on assemble IMF here. Similarly, for EPMD, we apply the GSM process on each extractor assemble IMF, and then finally we obtain the first EIMF here, which is orthogonal to each other. Now, this is in our study, we also had some comparison with the other signal processing techniques. And in the morning session, in the first session, we discussed about the approach using the wavelet transform. So as for the comparison, we have also implemented the discrete wavelet transform in FPGA. And this is what it is illustrated here. So we have actually applied the filters, high pass filters and the low pass filters, so as to get the signals of the approximate and the detailed one here, right? And this is the complete FPGA implementation for the technique here. In fact, this is the complete approach, and this filter part, it is actually illustrated in this inset blocks here. It is this one. And then we have also the implementation of EMD and orthogonal EMD on FPGA. So it is this block here. So as I said that you get a signal, right? And then this will have the extraction of IMF. So as upper envelope and the lower envelope. So in this block, you have this one where you have the comparison of the maxima and the minima, all that, and then storing the register and so on. We do that part, and then we obtain the A plus B or A minus B. That is for the minima, mean extractions and so part. And then we have applied Hilbert here, and finally we get the signal out of it here. This is another one, another step actually, which we had it in a FPGA for extracting the upper envelope. So it just shows the inner block of the FPGA here. So we have the storage of the data signal, I mean, in the registers, and then determining the maxima and the minima here part, and then again same way going to the next stage. So all that part we have done it here, and then finally we get the upper envelope. So same way we do it for lower envelope as well. And as you can see here that we get a signal, we have local maxima, local minima between the two samples. This part, we take the mean out of it, and then we check whether this is applicable, whether this signal is candidate for IMF or not. For that, we apply this decision actually, right? And that decision, we take it into account whether we want to know, because as I said that each IMF should be a monotonic frequency component. So we test that part here. And then because in the past there had been some study reported on islanding using the rock curve, that is the rate of change of frequency and rate of change of that is the phase angle deviation actually. So we have these techniques, rock curve and the rock pad, design in the FPGA because we wanted to have the comparison as well. So we have these two techniques also implemented in FPGA here. And next, as I said, that one part is the detection of your event, right? And second part comes to classify those events. So thus, for the even for the real-time classification, we have implemented the least square support vector machine in FPGA. And this is the complete block diagram for implementation of LSSVM here. So what we did actually for classification, we have obtained the features which were extracted from decomposed IMFs using EPMD techniques, and same way we did it for EMD and EMD as well. And these features, vectors, they were stored here in the ascertaining data set in the internal memory. And then we had also test data set by another set of the memory. L part we did it here actually. And next one, with those the signal processing techniques and the machine learning LSSVM technique being developed in FPGA, then we had some real-time and detection. And this is the first slide here for the result analysis. So in fact, this one is the case of a simulation result. In fact, it's for the case of non-islanding event. So we had it actually because here you can say this is a non-islanding. So we have actually some disturbance, which is a load disturbance here. So suddenly we have actually a load reduce amount. All right. So we can see that we have a load disturbance. So and thus we can see that there is a dip actually here, right? So because of the load disturbance, we have increase, right? So there is a dip in the voltage profile of the voltage signal here, and that is the voltage variation profile here. Then with the different techniques, this one refers to the discrete wavelet transform. If I guess, I'm not sure about it, but I think this is a discrete wavelet transform, and then Hilbert on conventional IMF, and then Hilbert on orthogonal IMF here. So as you can see that the moment we had the load change here, the moment you had the load change, load disturbance applied, we are able to, with these three techniques, we are able to detect the instant here. All right, so we are able to detect the instant of some disturbance, which is of non-aligning type, but we are able to get that. The next one is the we have considered as sag, a voltage sag about 7%. So you can see that there is a dip in the voltage signal. and for this much time period. You can see that. And this detection of voltage signal here, it is now being performed using Hilbert and different EMD techniques and the wavelet transform. So you can see here that wavelet transform and then a Hilbert orthogonal and conventional IMF, they are able to detect the period of sag occurrence here. So we can know the instant the sag takes place, and then the instant the voltage profile improves. So we are able to detect these instants here. And this is the slide for notch detection in real time. So we have actually some physical event applied and then created a notch in one of the phase. You can see here that it is being observed here, right? And it is, you can see here that with this technique, this one, the wavelet approach is not able to detect the instant of the notch occurrence here. However, the EMD techniques, all right, both EMD techniques, they are able to detect the instant of the notch event in one of the phase signal here. So we can do that. So you can see that it is something at what instant it takes place, and the same way we are able to have the detection achieved at the same instant here, similar, right? And then we did some study with the noise added, and then with the same sag signal. So this is the voltage profile with the noise added, and same way you observe that wavelet technique, it fails to detect here. And then however the EMD techniques, they are able to have the detection of the uh, event during which we observe the sag occurrence here. So we can do that. Same way, we have some more study. This is the case of a large power mismatch. That means the power, active power between the source side and the load side. It is a mismatch. And for that case, this is the voltage, PCC voltage profile you observe, and then profile of the current from the inverter side, and then the grid voltage side. So this is the waveform. And with this condition, we have the islanding here, right? So we want to detect the instant. So as you can see, the grid current side, because the switch is completely open here, right? So this is on the DG side, PV side here. So with the different techniques here, right? So with the wavelet and the EMD techniques, so we are able to detect the instant of islanding event in real time here with the different techniques here, right? Then we also have the case for a zero mismatch power, right? And in this case, we observe, because since it is zero mismatch power, the PCC voltage, it is completely profile. So because there is no change in the voltage profile, because if you refer here for a large mismatch power, the voltage profile has changed here. But for the zero power mismatch, the voltage profile at PCC remains consistent here before the event and after the event here of islanding. And with the detection that we achieve using these three techniques, this is perfectly indicated here. And then we had some study, as in this case, this is for voltage signal. And then I think again, this is here you can observe that some more study we did it because for the voltage profile. So there is some, you can see that during this period there is a sag occurrence here. So we have some sag occurrence, and then the detection using the different techniques here. So we are able to have it. However, you observe that the wavelet transform completely fails to detect the instant of the sag here. Right. So in fact, in this case, we have shown the different use of different IMF here, because this is the conventional EMD using IMF 1 and 2, and this is the empirical EMD, and then with using IMF 1 and 2. So we have just shown the results using the different IMFs here. Then, as a comparison, this is the case, we have a load disturbance. So the induction motor load which we had it actually, so we have applied some load, right? So you can see that what is the change in the voltage profile you observe, right? And under this situation of load change, the detection using the different techniques illustrated here. So with the using EP assemble, energy preserving, assemble one, conventional and discrete wavelet transform. So all these three techniques is shown here. Same way for the 7% voltage sag here. You can see that discrete wavelet transform fails to detect the instant, the period of the sag. However, the conventional EMD, when you look at, they are not so accurate in the detection. However, if you refer to EMD, assemble, and the energy preserving, they are able to clearly, or that is the distinctly represent the period of SAG event occurrence here. So thus the EPMD and EMD, they are more, you can say it will be more reliable or accurate in the detection performance here with respect to these two techniques here. And then we had some, because as I said that we want to have the real-time detection, right? So now let's say that in the complete window frame of your signal, test signal, let's say that you have this is your sag here, and following very few seconds, all right, following very few seconds, let's say that there is some swell here. So if for the complete range of the signal, let us try to detect the sag event and as well as swell event. And that's what we have referred as composite power quality disturbance. And this is the case with the 20 dB noise. And the detection for, that means now you have this occurrence of two different events, sag and swell in the same time period, right? I mean, in the same, they are occurring in the succession in the time signal. So thus you can see that DWT, the performance of DWT, and then the performance of EMD and assemble and the energy preserving. So as we can see that energy preserving and assemble ones, so they can be said as more accurate in the detection of these two events here with respect to these two. And similarly, we did some more. So here we have changed the duty cycle of the converter, right? And as you can see, the voltage profile change, it is represented here. And in that case, what is the perform detection of using EPMD or EMD, it is being reflected here, right? However, DWT, you can see it is completely fails to detect this physical disturbance here. In fact, it's not a physical disturbance, but it is actually a control action related disturbance. Actually, it is because you are changing the duty cycle. So this is somewhat related to the control in the converter side. So it is not actually a physical, but control action related disturbance. Yeah. Next one, we have some, let's say another case, island detection for large or the zero power mismatch. And so here we have the case, this is the one, and this is the voltage profile and detection using the different techniques. So you have energy preserving, EMD, DWT, rock off, you have and rate of change of phase angles, and so all that part we have included, right? And this is with the case for large mismatch power. So because in fact this is for more or less 0 landing occurrence under the 0.5 power. And in fact this is for, because voltage profile remains same here. So this is for zero mismatch power. In fact, there is a mistake here. Actually, this should be for large. This is for large, and this is for zero mismatch power. So because the voltage profile remains same here. So as such, the detection under the zero mismatch power, you can see here that Rockoff completely fails to detect the islanding. However, Rockopad, it observes, and same way EPMD, EMD, and DWT, they also indicate the occurrence of the event here. But Rockoff completely fails to detect the instant of the event here. Then we had the same case with some noise added here. And we had it with 30 dB noise and 20 dB noise. And you can see here that Rockcob and Rockpad, they completely fail with the noisy signals. DWT also fails. However, significant detection can be observed using EPMD and EMD here. Same way with you can see that with the 20 dB more noisy signal, right? So performance using EPMD or EMD remains consistent here. But with the EMD, you can see that with more noise added. So you can see that EMD completely deteriorates here with more noise in the signal. However, DWT and these two techniques, they completely fail in this situation. And this is the some statistical analysis for the detection performance, and you can see that what is the percentage error in the terms of the energy leakage between the IMOs for the two techniques, assemble and the energy preserving. We had it for some simulator signals and then for experimental signals here, and you can see that with the case of energy preserving, the energy leakage is much lower compared to the ensemble EMD here, and same way even for experimental signals, the energy leakage percentage is much lower here. Then I move to the evolving disturbance, which is what the in fact more significant study that we had carried out. So, in fact, we had some initial study on IEEE 13 bus network, and it was as an offline analysis here. And you can see here that some of the critical cases we have considered for evolving disturbance. We have a fault, we have a sag or the swell, we have a capacitor or the load switching, and islanding. All these types of events occurring in succession. So you can see here that in a 3-bus network, uh, at this instant of time, there is a fault of 0. You can see here that it was at 0.31 second. So fault takes place here, and then fault remains, and fault is cleared here. So this is the time period of the fault occurrence, 147 millisecond. Following few cycles of the signal, let's say that there is a voltage swell, and right, and this is out another line. So this is another transmission line, TL1, and this is TL2 here. So another distribution network line. So there is a voltage swell you observe here. We have this signal on PCC, right? So but the disturbance we are taking at some other places in the network, but we observe the signal at PCC, point of coupling of DG and the main utility grid. So we have the swell observed in the voltage signal at PCC after few cycles, and then let's say that again after few cycles there is just some capacitor switching here. So you can see that within this time period, you have 3 different events: fault, swell, and capacitor switching here. And now when you look at using the wavelet, it completely fails to detect these events. Any of the event is not observed using wavelet. Empirical mode, conventional one, detects only swell, right? And you can indicate the capacitor switching. And then EMD also has some detection. However, if you refer assemble technique, that means energy preserving assemble, there we can know what is the fault duration, we can know about the swell duration, and we can also know about the capacitor switching. So that means using this technique, all the 3 events which occur in succession, they can be easily observe here. That is the approach with the assemble energy preserving assemble here. Similarly, we had one more study. In this case, we had the fault here, we had the swell, and we have the islanding, right? So because if you look at the signal property, signal characteristic of capacitor switching here and the for the case of island, they are very much similar, right? So we have that part, the fault, swell, and island. So you can see that using the EPMD technique, we can observe the fault, we could observe the swell, and we can also observe the islanding event here, right? But other techniques, they don't indicate the occurrence of these successive events here. Then we had some more study. As I said that the instant of capacitor switching, the signal property of capacitor switching and the island, they are very close. And for this case, we have the swell, and then we have the capacitor switching and islanding taking place in succession. And you can see here that using this technique, the capacitor switching event and the islanding event, they are clearly indicated. However, assemble EMD, it can only indicate the capacitor switching, but the islanding event is not so pronounced here. However, the DWT wavelet, it could only indicate capacitor switching, and that EMD has some indication of the events, but not completely here. Next, we had some experimental study, and you can see that this is the voltage profile. We had it. So we have the sag here, and then after few cycles, we have a sag of 35 millisecond, right? So we after few cycles, you have an island here, right? So thus this is an evolving event experimentally conducted, and you can see here that using the assemble energy preserving assemble, we can indicate it can detect the sag event and as well as islanding. Same way, even the assemble it can, but assemble does not clearly indicate the event of islanding here, right? Same way EMD, and then DWT, Rubkov, and so on. These three techniques, they are not so reliable in detection of the events here. Next one, we had it swell. So we had a swell, and then after a few cycles, we had the islanding here. And same way, you can observe that using energy preserving ensemble, we have clear indication about the swell occurrence, and then again even for island event. However, for other techniques, because EMD fails to detect the islanding, DWT could only show the islanding but not the swell, and so on. So, but Rakov does indicate, but Rakov completely fails to indicate the both events here. Right, so these all detections which we have performed, it is all in real time here. Then again, we had some more complex events, and then you can see that we had a sag about for 7% for 100 millisecond. Then after a few cycles, we had a swell for 100 millisecond, and then we have an islanding also here. And you can see that it is the energy preserving. That is the and even including EMD, but comparatively this is more sound effect. It detects the more clearly energy preserving one, so it indicates more clearly it has more clear indication about the sag, yes, then swell, and then even the islanding here. However, other techniques they are not so sound enough here. Then we had some study because we had once you had the detection, and then we want to classify them. And on this slide, we had the classification of these evolving events, but we had it performed offline. Right, so using the least square support vector machines, we had some disturbance, evolving disturbance, which included sag, swell, load switching, and island events here, right? And then we have obtained the statistical features, and we did some classification performance, and you can see that energy preserving had the maximum accuracy for classification. However, EMD the conventional one was little bit poorer here. And this is the case. This is the counter representation for the events, and you can see here that it is with using the technique EPMD, which had 98%. So we can see here that the counter representation for different events, sag, swell, load switching, and islanding occurrence here. Then this was the study as a offline, and then we had next as a real time. So here you can see that we had some successive events here, right? Because we wanted to have real-time classification. So we had a successive events, 3% voltage sag for 400 milliseconds. So here is a voltage sag. Then we had a 5% voltage sag, but for smaller duration, 100 milliseconds. Then we had a 5% swell of 100 millisecond duration. And we had a 5% swell for 50 millisecond duration. And then we had lastly the physical event, that is islanding event here. So with this time period, you can see it at 964.875 to 971. So this during this period, time period, we have all these events taking place here, right? Sag of different time periods, swell of different time period, and then again some impulsive response of islanding event. So you can see here that using the EMD technique, we could only have indication about the sag here. All right, we could only indicate sag, but it fails about the swell and islanding. Similarly, EMD, it indicates only about the sag and then one case of a swell, yeah, right, which is of much larger duration here. But 50 millisecond swell is not indicated, islanding is not indicated here. But using the EPMD technique, we have clear indication about the sag of longer duration and as well as shorter duration, which is of just 100 milliseconds. So we can indicate that also. Same with swell, again for longer duration, we have it 100 millisecond and up to 50 millisecond. We can also indicate that, and also it indicates the islanding event here. And these different events have been classified in real time. So we had the set of the, in fact, we have set class 1, let's say for the sag, -1, swell, we have set it +1, and then for islanding, we have set it, let's say, +2. And thus, these are the predefined class for each of the events. And here you can say that for the sag, it is -1, and then for this swell, we have it +1, and for islanding, we have it +2. So these are the indications of the predefined classes for the different events that take place in succession here. Thank you. So now here this slide tells you, gives you information about because this work which I had discussed, they are published in transaction, in IEEE transaction here. So one was in last year, in fact, and then another, it is just recently, last month it was published here. Right, so both are in the industrial electronic transaction here. So I welcome if there are questions if you like to have. Thank you.
Hello, sir.
Yes.
Sir, the classification was done here for real time, all quality management problems. So in that, what kind of classifier is used there, sir? You didn't mention regarding any kind of classifier.
Okay. No, I think here I had in my slide, I said it is least square support vector machine, LSSVM, this one.
Okay.
Yeah, I had it here. Yeah. So that is this slide just tells you because I have not discussed the least square support vector machine algorithm. That
Yeah, yeah.
technique mathematically I have not discussed, right?
Okay.
Because that technique we have not developed actually, but we have implemented the technique in FPGA. So that part I have included in my slide because that is not my contribution actually. So I have not included here. I can see.
So all the implementations in FPGA are using a system generator only, sir?
Yes, yes, yes. Xilinx blocks.
Okay, sir.
Yeah.
Thank you. Sir, in which FPGA it was done?
Yeah, there are different series models. So, but that I will not disclose at the moment because we have some more work to do
Okay.
at this part actually. So that part, that's why actually even in my slide, I have not indicated what is that part. I've not disclosed it actually.
Okay, sir.
Yeah, because
Because
we had the recent work published and then we want to plan some more.
okay.
So that we have not disclosed here. Yeah,
Mm.
sorry about that.
So what I suppose is special purpose FPGAs are necessary in case of power system real-time applications.
So this is the real-time applications we have
Yeah.
it actually. Yeah, we have it, and I can say we have the latest version. But
Yeah.
again, there are several of them. There are
Okay, sir.
several of them. Yeah.
Thank you. Thank you.
Any more questions from participants? Sir, we have some questions in
Mhm.
chat box, sir.
Okay. Just wait. Let me see. Okay, but
There
I
are
don't
so
see
many
it.
questions, but I will ask a few questions only here due to that.
But I don't see in the chat box. Okay.
Uh, Sir, in the right side, the corner is chat.
Ah, yeah, I can
So,
see this. Okay, I can see it.
so
Okay.
in which someone have
Okay.
asked.
Maybe I can address some of them. No problem. The first one, if I refer, I think the first that I could get it is what are the most recent advances and standard performance matrices of transient stability on nuclear power and hydro systems using stream learning machine. Okay. Uh, Now, you talk about the performance indices here, but and again for transient stability. Uh, in fact, there had been some techniques, right? Uh, but all those indices they had the use of signals which calculates the energy. So let's say that because we want to perform the transient stability of a rotor angle, right? And for the transient stability of a rotor angle, we can have the what is the energy level of first swing, because what is the energy level of the successive swing of the rotor angle. That is one approach we can have it, right? So but here you write about nuclear power hydro systems. Now and again you talk about stream machine learning. So uh, there I think do you mean to say some kind of deep learning approach, uh, but there but again in all the cases the basic calculation of the indices it will be from the energy of the rotor angle. That is one I can say here. Then you can have any technique, any deep learning approach you can apply, or any machine learning approach, I mean, you can apply here. That is possible. But again you add in your question nuclear power and hydro. But do you have any specific reason for including these two? If not, I can have it. I can address in my terms of it, because as I understand, because because in the case of because if I consider the example of a Nordic power grid, right? In the case of Nordic power grid, where you have the connection from Finland, where you have mostly the thermal power plants, then you have the integration with the Sweden power grid, and then you have the hydro power grid from Norway side, and then again you have it from Denmark side, and again you have it some from Russian part, and then Latvia, Lithuania, and so on. In their case, because of hydro dominated power source in Norway, and then again in the southern side of Sweden, it is mostly the nuclear, right? And then some part even in the case of Finland. So there is some issue related to low frequency oscillations, right? And that low frequency oscillations, and it is poorly damped. And for a very particular case of operating condition, we observe the low frequency oscillations arising from the generators, from mainly from the hydro generators. So that could be it could be example which you have it here. Then again, similarly, we also observe the low frequency oscillations from hydro generators, which are installed in the Austria, in that means in the Central European grid. So there also we observed it, and then some researchers from Graz University, they have done some study related to it. Actually, that I can say here. Maybe my answer was not perfect, but this is what I can say here. And then how should the prosumers be remunerated for providing voltage regulation as ancillary services, that means towards the reactive power and active power curtailment? Okay. Now this is because this is prosumers, you have to remunerate it for the improvement, right? And so in that sense, it is mostly as a decision based, as an incentive based actually. And we have some in fact you can say in some places, but not in a wide scale, but in very small practical case, such examples have they are being implemented. But you talk about the prosumers, yeah, you talk about how the prosumers will be removed, but again it is all based on decision actually. I must say that how much power you have in generation, how much power you have in demand, and then how much power they can remove. It all depends upon what is the energy traffic tariff level during that period. All that part we have to take into account here, I think. But you talk about the voltage regulation as an ancillary service. That is one part we can have it, but issues related to voltage regulation, it can be from the prosumer side, but that can be from the with the converter of inverters, actually control of inverters, you may say, I think. So that is possible. So I think it could be, but again this is a decision policy, but I have not worked on this part, on this question actually I have not worked, so I cannot say much
Uh,
on this part.
so there are so many questions, but
Yeah, yeah,
I
I
think
can see
that
that.
he is not here. Balmukunji,
But okay, okay,
Dr.
okay,
Balmukund Sharma.
okay, okay.
So,
Mm,
uh,
yeah, then maybe some other thing, kindly share that. Okay,
actually, he is
okay,
asking so many questions.
okay, okay.
Last question he asked about how we detect islanding when the DC supplying sufficient power to the load.
Yeah, that is what we have done it actually. Because when the DG supply, that means you have major power supply from the DG side actually, basically what it refers actually, no, rather than drawing power from the utility grid. So we have done that part. But you ask about best method. I cannot say about the best method, because if I say I will consider my method as the best method, right? Because we have done the real-time detection, but this is just for today, because research, it is a continuous process. So then it is possible that after 1 year or the 2 year, somebody else will come up and saying that their method is the best method. So it is very difficult
Right,
to say anything on this part actually.
right, sir.
I can, because we had tried to address some of the critical challenges in terms of, because yeah, because in our study we have considered sag, swell, momentum interruption, or the islanding in succession, right? But let's say that you have a sag and you have a swell altogether during the same time period, or maybe some overlapping time period. We have not done that part. So but again, this is a challenging issue, because when we had some comment from the reviewers, so they say that okay, this is your good work, but you also need to consider those physical events for which you have an overlapping time period. And we said that okay, that we can try in the future, because the evolved study on our evolving events actually we completed during the lockdown period actually. So and that time it was very difficult to have the access to the lab facility as well. So anyhow we did that part, but we plan to do it in future, I can say.
So, with this, thank you very much, sir, for delivering informative and wonderful talk about the real-time evolving disturbance detection. Sir, listening you always gives us new idea to work with. Hope our participants also enjoyed the talk and learn new concept and new ideas for their research work. Thank you very much, sir, for spare your valuable time from your busy schedule for this expert talk. Once again, thank you so much, sir.
Thank you, Dr. Vijay. Thank you very much. And
Thank
I think I have given the reference in my slide, so they have they can refer those papers and then get some more details about it. Actually, that is possible.
Sure, sir. Sure, sure, sir.
Yeah.
Okay, okay.
Thank you all
Thank
for
you,
once
sir.
again. Thank you very much. So Dr. Vijay, I can now log out. Or
Yes,
I
sir.
can.
Yes, sir. Yes, sir. Yes,
Thank
sir.
you very much. Okay, then. Bye.
Okay. So once again, thank you all. And tomorrow we will meet for our last day of FDP, that is day 5 at 10 a.m. So tomorrow we have 2 talks, and one talk is from stress management. And tomorrow we have to conduct one quiz also. The quiz will be the MCQ type, multiple choice questions, and there will be the total 15 to 20 questions will be there. And after that there is validation session. And one thing I want to remind all of you that you all of you have to give the feedback in your login. So there is a link in the participants login about the feedback of this FDP about the experts. And once we will update the attendance, and then your certificate will be generated automatically. Thank you, and we will meet tomorrow again at 10 a.m. Thank you. Uh, we will share today all the PPT links on your email ID. If any time, if any questions, you may ask. We will send the link for all recorded session till now. Okay, have a great day. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.